All right, this exam covers lecture number 1 to lecture number 6, similar to your midterm exam. It had 14 questions, and as you may see, the questions are weighted from 6 points to 11 points. So the maximum difference between two questions, the maximum difference between the scores of two questions is just 5. You would see some easy questions and some difficult questions. And I would recommend you to start from easy questions because those are answering those questions would take much less time compared to the more difficult questions, but the points are not, they are kind of similar to each other. So first, go over all questions one by one, then try to answer those that you find easier for you, okay? I will do the same. So here, question number 1 looks for axial force in element number 2. That's pretty much easy. That's one thing that I probably start with. Here it asks for stress in element number 2. Looks easy. Here it asks for what is the modular, which one has the highest modular of elasticity. You may answer that by just reading the question. So easy. Here it asks for determining the strain in one post if we have strain in the other elements. I think you had this in the assignment or maybe in the class, I'm not sure, but I remember this question. So it is something that you may have seen before. It's easy, but it requires several steps. So you may categorize that in, say, category 2. So maybe less priority. Here, again, we need to do some calculation. So I may say, after solving easy questions, I will get back to this. Here, it's just a conceptual question. What is the relation between deformations? We can answer that easily. Here, we need to determine the deformation. This is a question that I said you will see that in the exam. Okay, so you will see this question in the upcoming exam. This is a design problem. This is shear strain problem. This is, again, another design problem and another design problem. Here is thermal problem, which looks for change in the diameter after increasing temperature. Here is indeterminate problem. So this is a problem that requires time to find the answer. I will not start from that question, and I wouldn't recommend you to do that. Similar to that is this one. This is again indeterminate axially loaded problems, category number 3. Okay, so now after reviewing the questions, I'm ready to start from the easier one. Here, I will start from very first question, but you may start from others. All right, question number 1. Axial loads are applied with rigid bearing plates to the solid cylindrical rods as shown in the figure. F1 is 35, F2 is 10, F3 is 28, F4 is 39. Determine the absolute value of the axial load in the rod. By the way, your numbers will be different from the person next to you. Is that clear enough? Okay, so every student has its own number. Okay, so here we are looking for absolute value of the force. It's free body diagram problem. So I'm gonna cut element number 2, as we see here, put all forces and try to write equilibrium equation. Here, some of the forces in y direction will be used. If I start from top, I would have 35 with a negative sign. I assume downward is negative. There are 2 times 10, again with negative sign, plus 2 times 28 minus P2 should be 0. Okay, if I solve that, that gives me P2 is equal to 1 kips. So the answer of this question is A. Any questions for this? Clear? Okay, question number 2. Determine the absolute value of normal stress in rod 2. Okay, similar to the question that we had before. Instead of force, we are looking for stress. So in addition to determining force, we need to determine area and then divide force by area. All right, I'm gonna take out the free body part of that. So here, I'm gonna cut element number 2, put unknown force on the cut section outward from surface, use equilibrium equation. In x direction in this case. Start from left, negative 80. plus 2 times 140 plus F2 is 0. If I solve that, that gives me F2 equal to negative 200 kilonewton. Area. How much is the area of that rod? Simply pi diameter squared over 4. Diameter is 27 millimeter, and that gives me 572. So stress would be force over area. Okay? Force is 200 kilonewton, and I need to convert that into newton by multiplying that by 1000, and area is 572, and the stress would be negative 349 megapascal. So the answer is A. We have 4 different types of materials. We have a stress strain curve for 4 different types of materials. Which curve has the smallest module of elasticity compared to the other one? Which curve has the smallest module of elasticity? What is E? E is slope of the line of these figures. So here, curve D, this one has the smallest slope. So the answer will be option D here. All right, so let's solve this problem later. And this one, okay, conceptual question. For the picture below, which of the following statement is true? It actually looks for what is the relation between deformations of different rods. In this system, there are 2 facts. First, the system is symmetric. So when I pull it down, it is not tilting, it is not rotating. The structure is symmetric. Second, there is not any gap. As long as there is any gap and the section is symmetric, delta 1 is equal to delta 2. So option A. All right. Okay. Determine the absolute deflection of joint C relative to A if the cross-sectional area of the column is 6,000 square millimeter. Assume module of elasticity is 200 gigapascal. All right. How we can answer this? To answer this, we need to see what connects point C to A. In this case, element number 1 and element number 2 are connecting these 2 points. So I need to determine deformation of delta 1 and delta 2. Deformation of element 1 and 1, 2. Okay? So to determine deformation, we need to know length, force, module of elasticity, and area. These are all provided but force. So I need to determine internal force. Use free body diagram. Okay? Let's talk about element number 1. I'm gonna cut element number 1 somewhere between B and C. This will be the free body, and write down some of the force in the y direction. There are 2 times 125 force going downward, plus F1 is 0. Here, I assume downward is positive. It doesn't matter. You can consider upward or downward. The final answer will be the same. So F1 will be negative 250. Here, negative sign means that that force is compressive force. Okay. Now let's do it for element number 2. How can I cut element number 2? I should cut that somewhere between A and B, and which part of the structure should I consider? Bottom part or top part? The top part, because the top part is free, and I'm considering the entire top part of that, like this. Okay? So sum of the forces in y direction should be 0. I will say 2 times 125 plus 2 times 175 plus F2 is 0. That gives me F2 equal to negative 600 kilonewton, and we are done with the forces. Now let's calculate deformation in each rod. Delta 1 is FL over EA. I'm going to plug the values. So F1 is negative 250,000 newton. Don't forget to convert that into newton. Length is 4.2 meter, and I need to convert that into millimeter. So multiply that by 1,000. That is 4,200 millimeter. Module of elasticity is 200 gigapascal, which is equal to 200,000 megapascal. And area is 6,000 square millimeter. And that gives me negative 0.875 millimeter. Okay, let's do the same for the second element. For the second element, the force is negative 600, and the length is 5 meter. The denominator of that fraction is the same, and that gives me negative 2.5. How much would be the total deformation of point C to A? That would be delta 1 plus delta 2, which is 3.375, and the nearest answer is E, which is 3.37. All right, we might have mistakes in finding the answer. Just track those mistakes, find what's wrong, and try to avoid that. Okay? Design equation. I guess I solved this in one of the sections, so let's talk about this one. All right, I actually solved a problem similar to this in the class, but this is just I rotated the triangle 90 degrees. Let's see what we have here. A thin polymer plate PQR is deformed so that corner Q is displaced downward by a distance L equal to 0.7 millimeter. Determine the shear strain at Q associated with the two edges PQ and QR. Okay, we are looking for shear strain. For determining shear strain, I need to see how much is the change in the angle at that point. How much is the initial angle at Q? It's pi over 2. So I need to figure out a way to determine the change in the angle. Remember, generally, we have two ways to determine that shear strain. Sometimes we can determine the angle after deformation, and the change would be the initial angle minus the angle after deformation. So this is the way that we can determine the change in the angle. This is this case. Sometimes we can directly measure the change in the angle. Here we cannot directly measure the change in the angle. So let's determine how much is the angle after deformation, then I will subtract that from the initial angle. Does that make sense? Okay, to do that, I'm gonna consider a horizontal line passing from point Q prime, and I'm gonna consider these two triangles. Let me enlarge. I'm gonna zoom into that triangle so you might see them better. Here I will define two angles, alpha 1 and alpha 2. Can I determine alpha 1 in that green triangle? Yep, we can. We know how much is the height, we know how much is the width of that, so we can determine that. We can do the same for the yellow triangle. So alpha 1 and alpha 2 are known. If we know alpha 1 and alpha 2, we know how much is the entire angle after deformation. And then I will subtract that from the pi over 2. Alrighty, let's do that. In the green triangle, tangent of alpha 1 is, how much is the tangent of alpha 1? How much is this length? It was 120 millimeter, but it moved down by L. So how much is the new length? 120 plus L. And how much is the width of that triangle? 240. That's unchanged. So I will say alpha 1 will be inverse tangent of 120 plus L divided by 240, and that gives me 0.46598. Alpha 2, how much would be alpha 2? That would be 480 minus L divided by 240. So that gives me 1.10657. Okay, one note. Here, when you are subtracting two numbers which are close to each other, you need to use more digits. Here is the only case in mechanics of materials that you probably need 6 or 7 digits to be accurate. Here I used 5 or 6 digits. Okay? Other than this, 3 or 4 digits are sufficient in your calculation. So don't use all the numbers that you see in the calculator. Just pick up 3 or 4 digits. Other numbers are not necessary. All right. So in this case, I'm using more digits. So change in the angle would be pi over 2 minus alpha 1 plus alpha 2. And that gives me gamma equal to 0.00175, which is equal to 1750 microradian. The closest answer will be A. Questions?
On the test, you're going to give us our other angles also going to be 90 degrees. We won't have to figure out what it is.
If it's 90, I usually show that by, I will show that's the right angle. So.
But if it wasn't 90, we would do the same thing as far as the inverse tangent.
Yeah, if it's not 90, you need to figure out how much is the initial angle, and we can do that here. That would be 120 divided by 240 inverse tangent of that, and you can do the same for the other one. All right. Design problems. For the connection shown, the average shear stress in the 18 millimeter diameter bolt must be limited to 215 megapascal. Determine the maximum load P that may be applied to this connection. This is a very typical design problem. So I need to see how much would be the maximum force that those 3 bolts can carry. Here, there is not any information about the plate, so I'm not designing the plate. In the assignment number 3, I also provided you with the information about the plate. So in that case, you have to also design the plate and see which force is the minimum. Okay, this is easier than the question that I gave in the assignment. So let's calculate area. Here, for area, we have 3 bolts, and each bolt is subjected to 2 shear. So that would be double shear connection. And then area of 1 bolt, which is pi over 4, 18 squared. Remember, 3 is the number of bolts, and 2 is because the connection is double shear. And area will be 1523 squared millimeter. All right, let's put that into design equation. Shear stress is P over A, and that should be smaller than the allowable stress. So I can say that P should be smaller than area times allowable stress. So P would be smaller than 1523 times 215, which is 328,000 neodon. So once you are working with the megapascal and neodon and millimeter, the final answer of force will be neodon. The options are in kilonewton, so I simply divide that by 1,000, and the closest answer will be C, 328. All right. Okay, another design problem. This design problem has several steps. So let's review it together. The rectangular bar is connected to the support bracket with a 26 millimeter diameter pin. The bar width is 85 millimeter and the bar thickness is 25 millimeter. Each side of the bracket has the same dimension as the bar. The average shear stress in the pin cannot exceed 100 megapascal. The bearing stress in the bar cannot exceed 140 megapascal. And the bearing stress in the bracket cannot exceed 140 megapascal. Determine the maximum value of P that can be supported by the structure. Okay, here we have information about all 3 elements: brackets on side, pin on between, and bar on top. So we need to design all of them and see what would be the maximum P that each of these elements can carry. Once we determine that, the minimum value will be the answer of this problem, because that will be reached always, the minimum value reached, and that would be the failure of that structure. All right, let's start with the shear stress in the pen. Okay, for shear stress in the pen, I'm going to determine the area. Area will be 2 times area of 1 pen. Why I use 2 here? Because double shear connection, okay? And area of 1 pen is pi 26 squared over 4, and that would be 1062 squared millimeter. Shear stress will be force over area, so P over AV, that should be smaller than the allowable stress, or force should be smaller than area times allowable stress. Let's plug the values. Area is 1062, allowable stress for the bar is 100 megapascal, and that gives me 106.2 times 10 to the third neodon. That is equal to 106.2 kilonewton. All right, let's do the same for bearing stress in the bracket and in the bar. Here, I just need to do that I just need to determine the bearing stress in the bar, not in the bracket. Why? Why I don't need to do why I don't need to determine the bearing stress in the bracket. Look at the maximum allowable stress in the bracket and the bar. They are the same. It means that they are made from the same material. They have the same width. The width is 85 millimeter. They have the same thickness, 25 millimeter. But we have two brackets. So definitely bracket is stronger than the bar. So I need to design the bar because that would be controlling here. Does that make sense? So I don't need to repeat that for brackets. All right. The bearing stress is normal stress, and that the value of that follows from force over area. What area should I consider here? The area of bearing stress is always diameter of the hole times the thickness. Okay? So here, D times T. Diameter is 26 millimeter, thickness is 25, and that gives me 650 square millimeter. What would be the bearing stress for the bracket? Because we have two brackets, I multiply this value by 2. So the area will be larger and stress will be smaller. That's why I said that we don't need to calculate stress in the bracket. Okay? Normal stress will be force over area. This one should be smaller than the allowable normal stress. So let's write it in this way. P should be smaller than AB times sigma allowable. A sub B is 650. Allowable normal stress is 140 megapascal. And that gives me 91,000 neodon. Which one is controlling in this case? The second one. 91 kilonewton is smaller than 106, so that will be the answer of this problem. Questions?
Why wouldn't you use half the circumference for the area because it's a circle?
Mm-hmm.
So wouldn't that area actually be a little bit smaller than what the actual area is?
For the bearing stress, you mean?
Yes, sir.
The circumference will be always larger than the area of what I have considered here. This is what I discussed, and there are, I guess, 3 videos in the YouTube. Let me show it here. This is the cross-section of that hole. If I consider the circumference of that when the pen is pushing toward that plate, I need to consider half of the circumference. But I'm considering along this line. So that would be always smaller than the circumference. So that's more critical. That's why we consider diameter times thickness in the bearing stress. Questions? A solid aluminum with the modulus of elasticity equal to 70 gigapascal and the coefficient of thermal expansion equal to 22.5 times 10 to the minus 6 is connected to a solid bronze element. Aluminum rod has an outside diameter of 44 and bronze rod has an outside diameter of 124. The bars are unstressed when the structure is assembled at 30 degrees. After 300 kilonewton load is applied to flange B, the temperature increases to 45 degrees. Determine the normal force in rod 1. Okay, so it's, as I said, the most complicated question that you might see. We have temperature effect, we have force, the problem is indeterminate, and we need to solve that. I think everybody knows that this problem is indeterminate because we have 2 unknowns, 1 equation. Let me solve it here. Step number 1 is using free body here. The free body is shown there, so I can say that negative F1 plus 300 kilonewton plus F2 is 0. So that gives me F1 minus F2 is 300 kilonewton. Second step will be writing down the deformation as a function of force. So delta 1 will be F1 L1 divided by E1 A1 plus there will be thermal effect alpha delta T L. Okay, let me write it down and plug the values. So element number 1 has an outside diameter of 44, which gives me area of 1520. The temperature change is 15 degree. I will write it in this way, 45 minus 30. And the initial length is 2600 millimeter. Okay, so that will be delta 1. I will do the same for delta 2. Delta 2 will be F2 times 1 meter. The module of elasticity is 100 gigapascal and the outside diameter is 124. Coefficient of thermal expansion for that is 16.9. Okay, so once I determine that, I'm using the equilibrium equation, the compatibility equation in step number 3. And what is the compatibility of deformation here? Delta 1 plus delta 2 is 0. All right. So I'm going to plug the values, but to save time, I'm going to multiply both sides, but the largest denominator here. So that would be all right. So if I simplify that, that gives me 2.95 F1 plus F2 would be equal to, okay, so that would be the second equation here. And I'm going to combine that with the first equation to solve how much is F1 and F2. Yep, I'm looking for something which is wrong here because what I get is not the correct answer. So probably that is one thing that I missed. So here you are correct. It is not 700, it is 70,000. So that changes this one. Okay, yes, with that correction, what I will get is, yeah, I made a mistake. I thought that it's 700 gigapascal, which is 70 gigapascal. And if I solve that, that gives me F1 equal to 34.8 times 10 to the third Newton, which the answer is, the closest answer is C, 34.9 kilonewton. So one lesson that we learned is we need to read the problem statement carefully because it would be very hard to track what is wrong here, specifically if you don't write down everything neat and organized. If everything is in your calculator, it would be very hard to see what we missed here. Okay. What else? This is the problem. Did I talk about that in class or was it homework? So do you want me to solve this or something else? Let's talk about this. Okay. This is also a difficult problem because it requires several steps. Aluminum rod 1 and bronze bar 2 support rigid bar ABCD. The bar has a load P equal to 60 kilonewton at B and pinned at C, as shown in the figure. Find the downward deflection of rigid bar at A. Okay. Here, the problem is in determining because we have 4 unknowns and 3 equations. If we ignore the restraints at A, we would have 2 unknowns which are forced in bar number 1 and 2, and we would have one equation which is sum of the moments about about C. So that would be indeterminate problem, okay? So to solve this problem, I need to start from free body diagram. I'm gonna draw the free body here. So there will be 2 reaction forces over here, which I will ignore them because they don't play any role in my calculation. And I will ignore 2 associated equilibrium equation. I'm gonna put 2 unknown force in rod 1 and 2. The rod 1 force goes upward and force in element number 2 goes to the left because they should be outward from the cut section. So let's call them F1 and F2. And sum of moments about C. Also, in addition to that, there is a force P, which is 60 kilonewton over here. And I will write down some of the moments about C. All right, force P has the arm of 400 millimeter. I will consider clockwise as positive. F1 will be on counterclockwise, so I will consider negative for that, and the arm of that would be 750. And F2 would be clockwise, so I'm going to consider that as positive. How much is the arm in this case? It's 300 millimeter. Okay, so let's simplify this equation. I'm going to write it in this way. Here, I will divide both sides by this minus multiplier here. So that would be F2 minus 2.1 F1 is equal to negative 4P. All right, so this is step number 1. In step number 2, I'm going to write down deformation as a function of force. So delta 1 will be F1 times length, which is 600 millimeter, divided by modular plasticity and area. The modular plasticity of element number 1 is 200 gigapascal and area is 7T. So I will write it like this, 200,000 megapascal and the area is 7T squared millimeter. So that gives me F1 divided by 23,330. Okay? Similar to that, I will write down delta 2. Here I don't have any thermal effect. All right, so we wrote deformation as a function of force. And the third step, which is very critical in this problem, is using the compatibility of deformation. Here, how can I determine compatibility of deformation? We need to consider triangles. Let me draw the triangle over here. So once this element is pushed down, this deforms like this, and it moves like this. Okay? So we see two triangles here. One will be this triangle, and another one is this triangle. So I will call this as delta 1. Here there is not any gap, so I shouldn't be worried about gap. Here in this case, I can say that delta 1 divided by 750 is equal to delta 2 divided by 300. Is that correct? No, it is not. I'm missing something here. That's the trick about this problem. What I'm missing here. So if the element moves like this, bar 1 is elongating. It's getting larger, but element number 2 is getting shorter. So they have opposite sign. If I rotate that in a reverse way, one would be positive, the other one will be negative. So here, to be correct, I need to consider negative sign here. Otherwise, the final answer will not be correct. All right, so let me simplify this. I will say delta 1 is equal to negative 2.5 delta 2, okay? And I just plug the values into these equation. So that gives me F1 is equal to negative 0.14 F2. So this is the second equation that I was looking for. All right. Now I can combine these two equations and determine how much is F1 and F2. So F1 will be 59.26 kilonewton. Sorry, it's F2. with the negative sign, and F1 would be 8.3 kilonewton with the positive sign. Okay, this is not the answer. For this problem, we need to determine how much is the downward deflection of that point. So I need to determine how much is delta 1. And delta 1 is F1 divided by 23, 330. Okay, here, should I use 8.3 or what? It's kilonewton, so I need to convert that into newton. So I'm going to write it like this. 8,300 newton divided by 23, 330. And hope we can see one option here, which is equal to 0.356 millimeter. Let's see if we can find it here. So option D is the answer of this problem. Okay, so we have solved two problems which are kind of the most difficult and the most time-consuming questions in that exam. How many questions remained? This is easy. Yep, pretty much easy. Not difficult. Okay, let's do that. Let's finish the solution here. For the connection shown, the shear stress in the 5/16 diameter bolt must be limited to 22 KSI. Determine the maximum load P. Okay, it's straightforward. Shear stress is force over area, and that should be limited to allowable shear stress. How much is the area that we should consider here? Area would be 2 times area of a pen because that is a double shear connection. So I will write it like this, 2 times pi 5/16 squared over 4. So that would be 4882 here. And the unit is inch squared. And I just plug it into that equation. So I can say force, or P, should be smaller than the allowable stress times area. Allowable stress is 22 KSI, and area is, that is 1.07 kips, which I don't see it here. Okay. No, I forgot to multiply that by pi. Yep, that's my mistake. Okay, sorry. All right. And the final answer is 3.37, which, yes, we have it here. So that is the answer. Okay. Any question about that? 22 KSI, if I multiply that by squared inch, that gives me kips. So I can work with that. Yes, sir.
Why is it that we aren't considering it as 2p, where as you solved it, there's only 1p?
Okay, good question. It's all about free body diagram. Okay, so once we are solving the force, we need to see how much is the force that should be transferred through the pen. Okay, we shouldn't guess what is the force. We just need to use free body diagram. To understand that, let me cut this structure from once here and once here. Can you see that? I'm going to take it out. So for record, the question is why we considered P, not 2P in this analysis, and I'm explaining why we didn't do that. So if I take out, say, the right part of that, there is one plate, there is one force, P goes to the right. What else? What did we cut here? We cut 2 bolts, okay? So we need to put 2 forces on the cut section. There will be one force over here and one force over here. How much would be the magnitude of the force on each side? P over 2. That's why we consider this as a double shear connection, because 2 areas are sheared. If I consider 2 areas, how much would be the force that acting on those 2 areas? P, is it P or 2P? It's P. Okay? So I can consider one area of bolt and consider P over 2 as a force, or I can consider two areas on top and on the bottom and consider the P should be transferred. Here you don't see 2P. Remember, the force that is acting on the right side is actually canceling what the force acting on the left side. So one is action, another one is reaction. Okay. Free body diagram is very important, and that's why statics is prereq of mechanics of materials. A rectangular nylon with a modular of elasticity equal to 8 gigapascal, the Poisson ratio of 0.35, and the coefficient of thermal expansion equal to 25 times 10 to the minus 6 plate has a circular hole in its center. At an initial temperature of 21 degree, the plate width is 310 millimeter. The plate height is 230 millimeter. The diameter of the central hole is 75 millimeter. The thickness of plate is 26 millimeter. So lots of information. At a final temperature of 54, determine the diameter of the central hole. Okay. First, give you a hint. Without solving this problem, the answer is A. Why? How much is the change in temperature? 21 is increased to 54. Do you expect to see a very large change in the diameter? So the answer is A. But let's determine how we can do that. All right. Let me write down the information we have. Delta T is 54 minus 21, which is 33, okay? The initial diameter is 75, and I need to determine how much is thermal strain. The thermal strain is alpha delta T, which is, okay, so this is thermal strain. How much is the change in the diameter? So I'm going to write it like this. Change in the diameter would be thermal strain times the initial diameter. So that would be 0.6188 millimeter. And how much would be the new diameter? The new diameter will be initial diameter plus the change in the diameter. So I can say that is 75.06188. The answer will be A. Questions? Yes, sir. Okay, it's a good question. Can I ask you to repeat your question again here?
So if there's material on the top and bottom of a circular hole, why doesn't the diameter of the hole reduce as the material on top and bottom expands?
Okay, so consider one simple plate there. What happens if we increase the temperature in that plate? The entire plate gets larger, correct? Okay, now let me consider this case and put one circle with the same material within that hole. We just disconnect between the circumference of that circle and the plate. What happened in this case? What if I increase the temperature? Do you expect that disk get larger and the plate gets larger as well? If I increase the temperature, there is not any internal stress. So the entire element is stress-free. Okay? So the entire plate, circle with the same material inside that, gets larger. Now, let me remove that, say, circle from that plate. What happened if I increase temperature? Same as what I had before. So the entire system gets larger. Generally, if you increase temperature, everything gets larger. Everything, including the hole that we see there. Okay, that's why if you may had this experience before. You may notice that if one, say, glass is stuck in the other glass, what do? You increase temperature of the other glass and the hole gets a bit larger, so then you can remove the top glass from that. Okay? So the same is here. If we increase the temperature, everything gets larger. Okay? So the hole is getting larger. It doesn't matter if we have a material on top of that or on the side of that. Another question that we may ask here is what happened to the thickness of this plate? Do you see increment in the thickness or decrement? Everything gets larger, including the thickness. All right. Let's see how many questions remained. So we answered this, this one, this one, this one, this one, not these two. Okay,